Hello, and welcome to the lecture on 2.3. Today we're going to talk about how we can get information from a graph. So let's start with our domain and range. So first we need to recall what the domain and range are. The domain of a function f of x is the set of values x can take, and the range is the set of corresponding values f of x. Let's go ahead and do an example, starting with the domain and range. Okay, so suppose that we have this curve here, and we're looking for the domain and range. So remember, the domain is the x values that we can plug into this function. Remember, this function consists of a bunch of xy coordinates, where x would be your input variable and y would be your output variable. So y corresponds to the range and x corresponds to the domain. So if there is a curve at a particular x value, then that function is defined at that x value. If there is no curve at that particular x value, then it's not defined. So if we take a vertical line, if we intersect a vertical line at some given x value, so here the x value is 4, we intersect the vertical line here, which means that at 4, the curve is defined, and it's defined to have a y value here, so a little less than -4. Now, if we have a vertical line that's corresponding to an x value that is not touching the curve, then that means that x value is not within the domain of the curve. So here, at -4, at x equals -4, notice that we're not intersecting the curve anywhere. This means that -4 is not defined for this particular function. So how we find the domain will be anywhere we see the curve above or below an x value. So remember, this is our x-axis. At x equals -3, we have a defined function. At x equals -2, we have a defined function. Now, a way I like to do it is to take a vertical line, and we start at -infinity, the negative most x values, and we keep moving it to the right as x increases. Once we start to intersecting the curve, that's where we start our domain. So we start our domain here at -3. And then when we stop hitting the x values, when our vertical line stops intersecting the curve as we continue to move to the right in the positive direction of x, that's where our domain stops. So we keep going, we keep going, we keep going, and we are no longer touching the curve here at +12. So here at 12, we're not touching the curve anymore. Now notice I have a parenthesis here instead of a bracket, because at 12 we have an open circle, which means 12 is not defined. At x equals 12, it's not defined. So we go up to, but we do not include 12. We can do a similar process for the range, and we draw a horizontal line instead of a vertical line, because the horizontal lines have the equation y equals something. So now we start at the negative most values of y, and we move in increasing y direction, up in this case. So as we move in the increasing y direction, we touch our curve. We first start touching our curve at -4. So our range is going to start at -4. Note that we don't start at 0, even though that's where our domain, the first domain point starts. We don't start there. We start at the lowest y value for which we have a curve defined, and that would be -4. And we keep moving in increasing y direction until we're no longer touching the curve at all. We stop touching the curve here at 3. Now again, we have an open circle, so we're not actually defined. The y value is not defined at 3. It's defined up to, but not including 3. So our range goes from -4 to 3. Okay, I hope that helps. I want you to try one. Find the domain and range of this function. Okay, I will note that this arrow means that it goes up forever, but never crosses this dotted line. It gets closer and closer to the dotted line, but never actually crosses it. Similarly here, we'll get closer and closer to the value y equals 0, but never actually reach the x-axis. I want to do another example. This one not on the domain and range, but more on function values in general. So I want to find f of negative 1, f of 2, and an x value for which f of x is equal to 8. I also want to find g of negative 1 and g of 2. So this will be f of x, and then this will be g of x. So we're looking for f of negative 1. So we look for where our x value is negative 1 on the x-axis. X is negative 1 here. We're looking at the f curve. Since we're looking at the f curve, we're looking at the red curve, because that's our f curve. It's the function named f. And we see that the corresponding y value is positive 1. So f of negative 1 is going to be 1. Similarly, f of 2 will be when the x value is 2. So when x is 2, what is the y value on the f curve? So we look again at the red curve. We look for where x is equal to 2, right here. And the y value is 0. So f of 2 is 0. And then we look for f of x is equal to 8. So this one's a little bit backwards. Now we're looking for an x value that's associated with the y value 8. So here, remember, these are y values, and these are x values. So we're looking for which x value gives us a y value of 8. We look for where the y value is 8. We go to here. And now we're looking for the x value that's associated with this on the red curve. So we move over. We see that at y equals 8, we have this particular x value here. So it will be 5. In this case, x equals 5. Now I'm going to find g of negative 1 and g of 2. G of negative 1, from the exact same process, our x is negative 1, we're looking for the y value that's associated with the blue curve, because it's the g curve, the curve that's named g. So we go over to x equals negative 1, we see that the y value is 0, and we give a 0 here. Similarly, at g is g of 2, we're looking where the x value is 2, we're looking for the y value associated with the blue curve. So at 2, we look for the y value, and that's 4. So we get this. Now I want to note something really quickly here, because we're about to move into comparing functions. So I want you to look at these two curves, the blue and the red one, and I want you to see when one is greater than the other. Now when we say that, what we're looking at are the y values. So at f of negative 1, the y value is 1. At g of negative 1, the y value is 0. So the f curve is actually bigger than the blue curve at this particular x value. But they change at negative 2. So now over to the left of negative 2, you can see that the g curve is actually higher up than the red curve. And similarly, they change again at 0. So if we look at g of 2 and f of 2 is 0, but g of 2 is 4. So the blue curve is actually higher than the f curve here at this x value of 2. That's because they cross again at 0. So g is greater than f before -2 and after 0. G is less than f between -2 and 0. You can see the y values are lower than the y values on the blue curve are lower than the y values on the red curve. And this is the basis of what we're going to talk about next. Comparing function values, solving equations and inequalities graphically. The first thing I want to do is I want to recall something that we've recalled before. The point xy is on the curve of every function it satisfies. Now, we've recalled this before because we've done something very similar to this before, where we have solved equations and inequalities graphically. In this case, though, we're talking about where one function is going to be equal to or less than or greater than equal to another function. Solving equations and inequalities graphically. The solutions of the equation f of x equals g of x are the values of x where the graphs of f and g intersect. Now, you might recall when we did this previously that the solutions are going to be the x values. We're looking for the x values that make this equation true. The y value is just to help us, the y value is just the equality. So remember that y equals f of x and a different y will equal g of x for these two functions, and it'll map out a curve. What we're looking for is at what specific x values are their corresponding y values equal. The solutions of the inequality f of x is less than g of x are the values of x where the graph of g is higher than the graph of f. So remember again that y equals f of x is one function. We have a y value is the output of this function upon inputting an x value. G of x is a different y value because it's a different curve. Now, when those y values overlap for the same exact x value, then those two equations are said to be equal. Here, we're looking for when one of the y values is above another y value for the same x value. So suppose that we're given an x equals 0, then f of 0 is less than g of 0 means that the y value at x equals 0 for the g function is higher than the y value for the f function at x equals 0 as well. So what this looks like is this. This will be the equation graph, and this will be the inequality graph. We have a function like this. Say that this is our f of x, and this is our g of x. Then we would say that f of x equals g of x at these points, this point and this point. Note that these points are on both curves. So this is where f of x is equal to g of x. Because this y value associated with this x value is the same. You have the exact same ordered pair that's on both curves. So this x value would be a solution to this equation. Similarly, the x value that corresponds to this point, so the first coordinate in the ordered pair, is a solution to this equation as well, because for this x value, both f and g have the exact same y value, which means that f of x is equal to g of x for this particular x value. In this one, we're looking for a similar phenomena, except instead of where f and g are equal, we're looking for where f of x is less than g of x. So here's f of x, and here's g of x. Now we're looking for the points for which f is less than g, or where g is greater than f. So in this case, it would look something like this. F of x is less than g of x. And again, if you read it backwards, g of x is greater than f of x. So what we're looking for here is for what x values is the y value of g higher than the y value of f. So these intersection points are where they're equal, but we're looking for where the y value of g is higher. So for this particular x value, we can see that the blue curve, the g curve, is higher than the red curve, which means that this particular x value would be within the solution set. But remember, for inequalities, we're looking for an interval of solutions. So if we say that this is A and that this is B, we can see that f and g are equal at x equals A and x equals B, because that's where the two graphs overlap. But we're looking for where f is less than g. So we're looking at the x values that are between A and B. So our solution set in this case would be x is less than b and x is greater than a, or we can use the interval a to b. This would be our interval form. Let's go ahead and do an example now. Find the x values for which f of x is equal to g of x. For part A, let's say that we have x squared minus 1 is equal to 1 minus x squared. So we're looking at these two functions. Now we need to graph these because that's the whole idea behind this section, is that we graph them and find the solutions that way. So 1 minus x squared will look like, underline them so we know what color each graph is. 1 minus x squared will look like this. And x squared minus 1 is the reverse over the x-axis. So we have something like this. Now we can immediately see that the solutions for this equation are x equals 1 and x equals negative 1. That's the x values. Now another way to do this problem is how we did it before, where we subtract everything to one side and we graph that. So if we move everything over, add the x squared and subtract the 1, then we end up with 2x squared minus 2 is equal to 0. Now this graph, if we plot some points here, let's say that x equals negative 1, we should get 0. X equals 0, we get a negative 2. And x equals 1, we get a 0 again. So if we plot this graph, then we would have something that looks like this. So it's still a parabola, but it's stretched out vertically a little bit. Where 2x squared minus 2 is equal to 0 would be where we cross the x-axis. So our solutions would be here and here, which is at x equals 1 and x equals negative 1. And here we have x equals negative 1 and 1 as well. Negative 1 being where they intersect here, and 1 being where they intersect here. So let's look at the example x cubed minus x is less than or equal to x squared minus 1. And again, we'll do it two ways. I'm going to graph x cubed minus x in red. And to graph x squared minus 1, which is the same graph as the blue graph up here, we have something that looks like this, where they both intersect at this point and intersect here. Now what we're looking for is where the red function is less than the blue function. And we can see here that the red function touches the blue function, but it's actually greater than on both sides of where it touches. So at x equals 1, it touches, so we have equality, so we need to include that in our solution set because we have less than or equal to. So over here you can see that the blue curve, the y values of the blue curve, are higher than the y values of the red curve. Now, what we do is we're looking at a vertical line that corresponds to an x. And everywhere that the y value of the blue curve is higher than the y value of the red curve, that's going to be in our solution set. So we start at negative infinity, and the blue curve goes on forever, and so does the red curve. So we'll have all of the x values from negative infinity up to a certain point. Well, now we need to figure out when the blue curve stops being higher than the red curve. Well, it stops being higher at x equals -1, but we have less than or equal to. So -1 is included in the solution set, but then immediately after, the red curve is all of a sudden higher than the blue curve. So it does not satisfy this inequality anymore because the red curve is not less than the blue curve. It's greater than the y value. And then we go all the way up to here. We reach 1 where they're equal again. So we need to include that in our solution set. But we only include 1 because around 1, the red curve is still higher than the blue curve. So we end up with this solution set here. Now let's do the same thing over here, except we're going to do it the same way that we did it before. Get everything on one side and 0 on the other side. So what I'm going to do here first is factor out an x, and we end up with x squared minus 1. And then I'm going to subtract the entire term x squared minus 1 to the other side as well. So now we have 0 on the right and everything on the left. Hopefully you can see that we have an x squared minus 1 in this first term and an x squared minus 1 in the second term. So I'm going to factor that out. And we end up with x squared minus 1 times x minus 1. And then x squared minus 1 is a difference of squares, so we end up with x minus 1 times x plus 1. So this entire thing becomes x plus 1 times x minus 1 squared is less than or equal to 0. Now what this graph looks like, it's still a cubic graph, but we can we're clearly going to equal 0, 1, and -1. So we have here and here is where we touch the x-axis. Those are our y-intercepts. And our curve is going to look like this. And you'll have to trust me on this. But it looks like this. So now we're looking for where this function, the curve, is less than or equal to 0. Well, it touches 0 at -1 and it touches 0 at +1. It's below the x-axis to the left of -1. So we start at negative infinity, we go all the way up to -1, and we include -1 because we have less than or equal to, and this graph is equal to 0 when it touches the x-axis at x equals -1. So -1 is included in our solution set. And then it touches the x-axis again at x equals 1, but is never actually less than 0 on any interval. So we union just the point 1. All right, I want you to try one now. Graph each equation and find the solution set, where a is x squared minus 3 is equal to 2x. So here, on the left you have a parabola, on the right you have a line. And you're looking for intersection points because we're equal to here. And part B, x squared minus 3 is less than 2x. So you have the same exact equations, but now you're looking for where the parabola is less than the line. Increasing and decreasing functions. All right, let's do the definition. F is increasing on the interval I if f of x1 is less than f of x2 whenever x1 is less than x2 in I. F is decreasing on an interval I if f of x1 is greater than f of x2 whenever x1 is less than x2 in I. So what do I mean by these? Well, an interval I is just any sort of interval AB. So I'm going to go ahead and draw out an interval AB for both of these definitions. So let's say that we have the interval A, B. Now this is my interval I. Now whenever x1 is less than x2, so let's go ahead and plot that, and x1 and nx2, both of them on the interval I, then our function is increasing if the corresponding y value, f of x1, is also less than the corresponding y value of x2, which is f of x2. So notice that the y value of x1 is less than the y value of x2 whenever x1 is less than x2. So if x1 is to the left of x2, then f of x1 is below f of x2. That's what increasing means. And you can see that as we move from left to right, if we're moving from left to right in the direction of increasing x, our curve is going up. Then our function is increasing. Similarly, if we have this interval AB and we have an x1 and an x2, where x1 is less than x2 on our interval I, then we say that f is decreasing if f of x1 is greater than f of x2, meaning that the y value is higher for x1 than for x2. So notice here that x1 comes before x2 in the direction of increasing x, so x1 is less than x2. It's to the left of x2. But the y value is actually higher. So our curve is coming down. And we say that it's decreasing on the entire interval I if this is true no matter what x1 and x2 are, as long as x1 is less than x2. On this interval AB, if we choose any value x1 and x2, where x1 is to the left of x2, then f of x1 will be higher than f of x2. We say that the function is decreasing. Okay, let's go ahead and do an example. The following graph shows the mass of Captain Rex in the 15 years following the Clone Wars. Find the interval on which the function is increasing and decreasing. So here's our graph. This point will be the next topic of discussion. So we have the 15 years following the Clone Wars. We're looking for where this function is increasing and decreasing. So on the interval from 0 to 11, we can see that our curve is going up. And this is true because if you draw a vertical line, again corresponding to an x value, as we move from left to right, you can see the curve rising. But then it stops at year 11. So at year 11, it stops rising, and then it starts to come down. And that means that the function is decreasing. So we would say that we're increasing on the interval 0 to 11. Now, we use parentheses here when we're talking about increasing and decreasing. I can't really explain why until calculus. Once you get into calculus, you'll learn why we have parentheses here instead of a bracket. But for right now, the only thing I can say is that we're not actually increasing at this point. The height of the function is not changing here at this exact point. Everywhere else, we're increasing. And we're decreasing on this function from 11 to 15. This graph is talking about his weight. His weight is increasing on the first 11 years after the Clone Wars, and then it decreases for the last 4 years of that 15-year span. Next thing we're going to talk about is local maximum and minimum values. Now let's start with definitions of local maximums and minimums. The function value f of a is a local maximum value of f if f of a is greater than or equal to f of x whenever x is near a. We say that f has a local maximum at x equals a. The function value f of a is a local minimum value of f if f of a is less than or equal to f of x whenever x is near a. We say f has a local minimum at x equals a. So what I'm talking about here is, suppose we have something that looks like this. Then this point here would be called a local maximum. And this would occur at x equals a. Now, this definition, whenever x is near a. So if we enclose a in an interval, and it sort of depends on the function how tight this interval needs to be, but it can be as tight as necessary, and it can be very loose depending on the function. We can see that if we take any x value, any other x value, within this interval, so again, this red line will correspond to some x value, but we can take any x value within this interval, we can see that the corresponding y value is lower than f of a. The y value f of a is higher than the y value of every other x value that's near a. So this is the highest point, hence why we call it a local maximum. Now we say that it's local because it's possible that there might be other x values that are higher. Like suppose, for instance, that this graph went up like this. This would still be a local maximum because it's a maximum in its general area. Now a local minimum is sort of the opposite. Suppose that we have something that looks like this. And we would say that this is a, this x value here is f of a, and we can create an interval around a, and for every x value that's within this interval, we can see that f of a is going to be lower than the corresponding y value. So this would be a local minimum. Let's go ahead and do an example. Find the local maximums and local minimums of this function. So suppose that we have this function here. We're looking for local maximums and minimums. We can see we have a local minimum here because it's the lowest point in its general neighborhood. Even though this point is lower, it's not in this general area of the graph. So at x equals -2, there's a local minimum of -3. Now you might ask yourself where I got this -3. It comes from the corresponding y value. So at x equals -2, we have a y value of -3. So -3 is the actual value of the minimum, and that minimum occurs at the location x equals -2. At x equals -1, there's a local maximum of 2. So here, at x equals -1, we have a corresponding y value of 2. And then, of course, we also have another minimum. At x equals 2, there's a local minimum of -4. Now, here again, at x equals 2, the corresponding y value is -4. So the local minimum is -4, and it occurs at the location x equals 2. Try one. For the following function, find a, where the function is increasing, b, where the function is decreasing, c, the local maximums, and d, local minimums. So here's your function. Now for part A and part B, what you're looking for are intervals. You want to find the intervals where the function is increasing and the intervals where the function is decreasing. For part C, you need to find the location of the maximum or minimum, and you need to find the value of that maximum and minimum. All right, that's going to be it for today. I will see you all at the next lecture.